Okay. As we proceed forward, we're going to be talking about heat of fusion and heat of vaporization. Two ways you can measure that. It's what or what. Okay, that's just heat, just joules and kilojoules. But that's tied into your heat of fusion or vaporization. Okay, so if we're talking about a heat of fusion, it's either measured in one of two things, kilojoules per mole. Okay, this is what we had wrote down on Friday. And heat of vaporization, oops, and then joules per gram as well. So it's either one or the other, kilojoules per mole, and then joules per gram as well. That's what we're referring to when we're talking about heat of vaporization, heat of fusion. It's labeled in one of these two. Okay? Okay. Okay, so heat of fusion, it's either this or that. Okay? Same thing for heat of vaporization. It's either measured in kilojoules per mole or joules per gram. When they're measured in joules per gram, when it comes to those 5-step problems, it's much, much easier to deal with. Okay, and we'll illustrate one of those. If you have this graph here that was handed out to you last week, should have like page 436 or something to that effect. So I want you to pick a metal like platinum, gold, silver. So gold. Okay. So it has to be a pure metal because we don't have any other numbers to go by as far as heat of fusions or vaporizations. What I will put in the drop folder is a table that looks like this. And it has all these values on here, but they're measured in kilojoules per mole. So we are going to show you how to convert them to joules per gram. And then when you do those 5-step problems, it's much, much easier to deal with. But first of all, we had said we're dealing with the element gold. Okay? So in grams, how many are we going to eventually raise to vaporize? How many grams?
21.
How many? 21. Okay, so we're going to take 21 grams of gold, and we're going to go through the different phases, and we're going to use this as our roadmap, that page 436 that looks like this, that has that information on there. Okay? So I'm just going to write some numbers up here. We need gold's melting point and gold's boiling point. Okay, so bear with me for just a moment. Okay, melting point is 1064. Okay, that's degrees centigrade. The boiling point then is 2808. Again, degrees centigrade. So then we need a specific heat. And I suppose I could put equals in here. Specific heat for gold then is 0.129. 0.129 joules per gram degrees Celsius. And this is why we want to be able to show you to convert kilojoules per mole into joules per gram, because these are already measured in joules per gram. So it's much, much easier to do that, but you have to convert them first. So this is for liquid. So for solid specific heat, okay, I'm going to go 0.135 joules per gram degrees Celsius. And then for gaseous, gold, or the specific heat. 0.85 joules per gram degrees Celsius. Okay, so this is all information that would have to be given to you. There's nothing here that you have to calculate yet. This is all has to be supplied to you. So there's nothing, oh my gosh, what do I do? What do I do? No, this is all given information. Okay, now we're going to show you how to convert kilojoules per mole into joules per gram. All right, so in order to do that, okay, this is where these numbers are coming from. Okay, and I just didn't have enough time to maybe copy these. I was going to put them in the, perhaps put them in the drop folder. Okay, bear with me for just a moment. So we got to get down to gold, and it doesn't have these specific heats for solid and liquid gold, but they're probably pretty comparable to that. So here's your element gold along the top. Okay, so as we mentioned, these numbers have to be given to you. The melting point, as we said, is 1064. There's gold's boiling point, okay? And here's your specific heat in joules per gram degrees Celsius, which was 0.129 we put down. And notice here's your heat of vaporization, and here's your heat of fusion. And it's given in kilojoules per mole, but we want it in joules per gram, okay? So it's just a quick couple conversions, and you've got it in joules per gram. Okay, so let me write these numbers down. We've got 12.4 and 324.4. Okay. Now, again, those are measured in what? They're measured in kilojoules per mole, okay? And again, the reason that we want to convert them, not only does it make more sense in that 5-step problem, but what is your specific heats measured in? They're joules. So we want to get that kilojoule per mole in a joule per gram. All right. So 12.4, this is a known substance, so 12.4 kilojoules for every mole. Okay? You can do one of two things, and I'll show you how to do that. You can actually skip a step, because notice we want that in joules per gram, so we got to get rid of this kilojoule and into just joules. So, how many joules are in a kilojoule? 1,000. Okay? So then, for every kilojoule, you get 1,000 joules. Okay? So these are now gone. We're in joules per mole, which isn't quite what we want. We want joules per gram. Okay? So since this is a known substance, we can take the atomic mass of gold and use a molar mass. So if moles is on the bottom here, this is something that we haven't done before, where does moles go to cancel that out then? It goes on top. Usually when we see these variables, we go to the bottom, but since this is on the bottom, for every mole of our known substance, which is gold, what's the atomic mass for gold? Well, of course, you'd look on your table, and it's about 197. Okay? So 197, we'll just leave it at that, grams. Okay? So, what do these moles do to one another? They cancel each other out. Now you've got joules on top and grams on the bottom, and that's what you want. That is a heat of fusion that's much easier to deal with. Now we've got it in joules per gram. Okay? So we also have to do that for the heat of vaporization. And this is what you can do to skip a step. You can it's not that you're skipping this conversion, but in this case, if we're starting with 324.4, what did we do there? We had 324, but if we take that decimal back out, what did we do? Right, because that's what we do anyway, right? We multiply by 1,000. Does this make sense so far? So now you've got that in joules now. And we still have to do the same process. But we don't want you to forget that. Okay. Then how do you get rid of this mole, just like what we did here? Put it on top, and then 197 goes on the bottom. These cancel each other out. Now you're in joules per gram, just like we are up there, and that's a little easier to deal with in this 5-step problem. Okay, left side. We good so far? Middle. Okay. So 12,400. We're just taking them 2 times each other. So 12,400 divided by 197. 62.94. 62.94 joules per gram. Okay. Then on this bottom one, 324,400 divided by 197. That gives us 1646.7. 1646.70 joules per gram. Okay. So then this is also given information you would have to be given, or at least be able to have this number to calculate that. Okay, so what do we say? 62.94. And heat of vaporization was 1646.70. Okay. So should we just start at room temperature with our 21 grams of gold? Okay. So then that's probably somewhere around, we'll just say 40 degrees Fahrenheit, or excuse me, Celsius. So we need to change this from 40 degrees centigrade, okay? Because it has to be below your melting point, and if we're going to vaporize it, it has to be above your boiling point. So how high are we going to raise this temperature? 3,000? Just 3,000 only? Okay? Can we erase this? Okay? So this is where your graph, that page 436, will help you. Now we have all the given information that we need, and a problem would say something like this. How much heat energy is required to change 21 grams of gold from 40 degrees centigrade to 3,000 degrees centigrade? Then you'd have to be given the melting point for gold is 1,064. The boiling point for gold is 2808. Liquid gold, solid gold, gaseous gold. These are your specific heats. Then here's your heat of fusion and vaporization. Okay, so just like you see on that table on page 436, okay, so we're starting down here at 40 degrees. So eventually we're going to raise that up until we hit the melting point, which is 1,064. Okay, so I think the work is also illustrated here on page 436. Is this something you want to tackle on your own, or do we want to work on this together? You tell me. Okay. So just like it says in letter A, we've done a problem like this. It was but water though. In step A, it says the ice, but we're going to replace that with gold now. So in letter A, okay, the gold must be warmed to its melting point. Okay. So we've got 40 degrees centigrade up to 1064, because this is about what temperature gold will go from its bars to a flowable liquid. It's probably pretty thick, viscous fluid, but it still, nonetheless, is beginning to melt. So your formulas, remember your steps 1, 3, and 5 are the same. Okay, so steps 1, 3, and 5 all have the same formula. Q equals mass times specific heat times change in temperature. Okay, does anyone remember what steps 2 and 4 were? Or if you had that wrote down.
Mass times heat fusion.
Okay, so this one is mass times heat of fusion, and this one is mass times heat of vaporization. Okay, so in our first step, what variable is going to be seen the same 5 times in a row? Why are you right when you say 21? Because that's what we started with for a mass. Okay, so our first quantity then, or Q1, equals 21. Okay, what is the specific heat for solid gold? Okay, here it is, 0.135. And we also have a change of temperature, which is, okay, and you're right, but how did you get that though? Yeah, you're subtracting, excuse me, where you finished from where you started from, okay? Remember, it's temperature final minus temperature initial. So 1064 minus 40, and you said it's 1024. So you can write it like this, or you can put that 1024 in there, because that was the change in temperature. Okay? So that gives you Q1. Okay? So what does it say in step B then? Remember, it's not ice anymore. That was the example they gave. So we would say the gold must be what? Gold must be melted. The entropy of fusion and heat of fusion is the same thing. Okay? If it was water, it's 334. But that's not the case because we're dealing with gold. So as you said, 21 will be utilized 5 times. And the heat of fusion for gold is what? 62.94. And that gives you Q2. In other words, we're right at this plateau. Okay? Then we're going to add more heat to it. And in this case, we're going to go all the way up to 2808. Okay? So in this case, this was Q equals mass times heat of fusion. Now we're going up again in step 3. So Q equals, again, mass, specific heat, and change in temperature. Who's lost? Okay, so just like it explains in this table, we're on the 3rd step. And in liquid, yep. So in step C, the gold must now be heated from, if it was 0 to 100, what do we know about water? That's water's blank to 100. Melting point to boiling point. But in this case, again, we're dealing with gold, so we subtract the melting point from the boiling point. That's your change in temperature. Okay, so 21 times the specific heat for liquid gold, which we said was 0.129. And then what's finally our change in temperature by subtracting these two?
1784.
Okay. 84 or 44?
84.
84. Okay. Okay. You want to try to wrap up the rest yourself now, or you want to keep working together? Okay. So then we're leveling off again. Okay. This is Q equals mass times heat of vaporization. So therefore, we're at letter D now. So you could say A, B, C, and D.
It's 1744.
Oh, okay. 1744. Okay. So what does it say in step D? The gold must now be vaporized. The entropy or the heat of fusion for gold would be which one of these variables? $1,640. Okay, because it has to be per gram. Okay, so that's why making these conversions is so much easier when you get to this. Otherwise, you don't have something like this to deal with. You'd have, that starts out at, what was it? You'd be using 12.4 kilojoules per mole. So if you have 12.4 in here, that really doesn't help you out. But now, since you have it in joules per gram, it's much easier to deal with. And the heat of vaporization is 1646. And that gives you a set number. And then finally, and if you choose to maybe write this on an evaluation to help yourself out, notice that when you have an incline, every time you do that, there's a temperature change. Right here in step 1, right here in step 3, and then right here in step 5. Now, where is this stopping approximately? No, our boiling point was right there at 3,000. So then that's where we're going to stop adding heat to it. Okay. 21. So which one of these specific heats do we use now? Why are you right when you say this one? Because that's the gaseous specific heat. 0.185. And then what is our temperature range? 192, maybe? Is anyone confused where 192 comes from? Again, that's subtracting that number from that one. So 192. And yes, you're going to get really, really big numbers, but you got to remember, you are vaporizing gold. It's going to take a lot of energy to do that. So once you get all of these, then you add it all together and get one really, really, really big number. Okay. And I was hoping the goal was to correlate what you have seen with water in this graph and comparing it to a different substance, in this case, gold. Okay? Same process, same equations, but the mass is different. Of course, the specific heats are different. And of course, the heat of vaporization and fusions are different. Otherwise, solving it is the same way. I'll have your first paper tomorrow. Okay, so I can certainly get that information to you. Or I have it with me. Maybe you'd rather have me pass it out now while we're here together. Okay, so I'll just go ahead and pause this for just a moment. Okay, number 3 and number 5 are 5-step problems. So you're going to need and utilize this graph. It will help you because it gives you the boiling points, it gives you the specific heats, and it gives you the heat of fusions. Okay? So you just follow that path. Of course, you're going to get a different answer, but the way you get there is the same. Like, for instance, in number 3, you're going to use 24.5 grams of water, or H2O. You're going to use that 5 times. That goes here. Okay? You have somewhere on here, it gives you the specific heat of solid water, specific heat of liquid water, and a specific heat of gaseous water. Then it also gives you the heat of fusion in joules per gram and the heat of vaporization in joules per gram. Okay? So again, just use this as a roadmap. Okay? Then go ahead and pick one problem and we can work on that together. But before I go any further, can we erase this? Is there something that you feel that you want to go over? Otherwise, speak now or else it's going to be erased. Okay? So you can go ahead and pick one and we can work on that together.
Why does CP stand for
Specific heat is C subscript P.
Is that just how it is? Why would they not just use an S?
I don't know. It's just how it is. Yes. Okay. Yes.
You just do step 2.
Notice in number 1, there's no temperature range. So you know it's not a 5-step problem. And it's giving you in kilojoules per mole. Okay? That's water's heat of fusion. So what you had asked, is that just step 2? Yes, that's correct. But the only difference is it's measured in kilojoules per mole. But you don't have to do that conversion. And here's why. Okay? Because it's saying calculate the amount of energy required to melt. So that's going to be measured in heat, the heat energy, which is labeled in what or what? Joules or kilojoules. So we have a kilojoule on here, but it's just given in moles. But it's also a known substance. So therefore, you're going to have your periodic table. So for number 1, when it says water's molar heat of fusion is 6.009 kilojoules per mole, calculate the amount of energy required to melt 7.95 times 10 to the 5th grams of ice. So in this case, you probably just want to say the answer is going to be given in kilojoules. So in this case, we've got 7.95 times 10 to the 5th. Or if you just wanted to write that out as, what is that, 79,500? 795,000, okay. Trying to picture how many you go through. Do you want it like this or wrote out as 795,000? This works. Okay. So since this is grams of ice, we know that that's a known substance, so it's grams of this. Okay? So notice we've got that gram in there. So we're going to have to get rid of that somehow. But again, this is a known substance. So therefore, if we want to get rid of that gram. Yeah, we're going to use that. So for 18.02, where do you suppose that came from? That's the mass of water, okay? And then what would go up on top? That'd be your mole of water, okay? So this gram canceled out that one. Actually, I should have put H2O there. Now, we've got to get rid of that mole, okay? So what did we do in like this 5-step problem to get this to joules per gram? We need to get rid of this mole somehow, but you have one number that has kilojoules per mole in it. No. Say that again. So 6.009, and that's kilojoules for every what? So what do these moles do to one another? They cancel. And then what are we left with? Kilojoules. And that's a form of energy. Yep.
So that's the answer.
That's the answer. Yep. You know it's not a 5-step problem because it's not asking you to change states. Because in problem 3 it says change grams of ice, which is below -7, below its melting point, to steam at 145 degrees. Okay? But there is a temperature change in number 10, but we're just saying to raise the temperature. So it's just Q equals mass times specific heat times change in temperature.
265,000 watt.
Sure. And then for number 10, the specific heat for iron is 0.444 joules per gram degrees Celsius. You're going to need that number. Number 10, you're going to need that number. Okay? All right. The reason that this is probably confusing, difficult to deal with, because we haven't spent a lot of time on it. Time is running short, and we're trying to get this conveyed to a possible way that you can learn it and yet get through it in a timely manner. Okay, we'll catch up to you next time.